Hi everyone, my name is Sarah Gaballah, and in this talk I will present to you TOBBs, a new anonymous publish subscribe protocol that provides provable privacy for both publishers and subscribers. In this protocol, we provide a solution to the problem of anonymous multicast communication in public groups. Applications like microblogging, newsfeeds, and forums are examples of multicast communication in public groups. In these applications, users communicate based on mutual interests, where anyone can join the group at any time. Usually, no personal connections and trust between the users. The publish-subscribe messaging model fits these settings, which makes it suitable for the communication in these applications. In the publish-subscribe model, there is a broker which acts as an intermediary between the publishers and the subscribers. The broker receives the messages from the publishers and forwards these messages to the interested subscribers. The problem here in this design that the broker knows a lot about the users and their interests. If the broker is malicious, it can collect data about the users and sell this data to other third parties or reveal the data to governments, which could be very dangerous, especially for users like political and human rights activists. Therefore, there is a need for enabling the user to communicate anonymously so they can hide their interests from the broker, other users, and even from a global adversary who observed the whole communication. Here we consider a threat, the following threat model. We consider an adversary that can observe traffic on every link, insert, delay, drop, modify packets, corrupt some of the servers, control many users, join all the groups, and get all the published messages. And our security goals are sender and receiver and observability. And that means the adversary can't identify the actual sending and receiving activity of the honest user. To the best of our knowledge, no existing protocol can protect against this threat model and achieve these security goals. There is no open sub-communication solution with a strong, provable privacy guarantees for both publishers and subscribers. So we can see here in this table that some protocols require trusted group members, others don't provide both sender and receiver anonymity. We can find some anonymous group communication systems that offer strong cryptographic security guarantees and hide metadata efficiently. But the problem in these systems that they support anonymous broadcasting, which means high bandwidth overhead on the client side in case of application like microblogging. So here in TOBBs, we provide a solution for this problem and try to defend against the mentioned threat model, and we want to achieve the described security goals. Our system consists of three phases: private publishing, revealing the messages by grouping them by topics, and the third one is private retrieval of messages. And the first one is based on distributed point function, and the third one is based on information theoretic PAR. We will discuss each one in detail in the next slides. The first phase, private publishing, to write the message privately, the user generates in secret shares, where n is the number of servers. Since we consider an adversary that can observe the whole communication, can launch active attacks like replaying or modifying messages. Here, each share needs to include a timestamp and be encrypted with the receiving server's public key. The user sends the share to each server, and every server expanded the received shares to vectors with a length equal to the length of the database. And then the server adds the vectors into the database state. And then we move to the second phase, managing the published messages. To reveal the published messages, the servers share their database states and combine them. And then after revealing the messages, the servers group the messages into blocks based on their topics, like here. In the third phase, private subscribing, we have two parts: private subscription registration, and here this part, the users create a BIR query. The BIR queries don't reveal anything about the user's interests if at least one of the servers is honest. And then the user prepares as a subscription request, which contains randomly chosen shared secret and the BIR, and then both are encrypted using the public key of the server. Then the user selects one of the servers to be its primary server and sends all the subscription requests to this server. This server can decrypt the messages because the messages are encrypted using the public key of the server, the corresponding servers. So the task of the primary server is to just forwarding the requests to the corresponding servers, where the messages will be decrypted and stored on these servers. So here in the second part, private messages retrieval. To retrieve messages, each server computes a response for each stored subscription request and hide the content of the response by XORing the response with the shared secret. The servers send the responses to the primary server. The primary server XORs all the responses together and sends the final result to the user. The user reveals the published messages by XORing the received reply with all the shared secrets. Here in this slide, we present the results of evaluating our system in terms of network overhead. The goal of our evaluation is to investigate the impact of using a distributed point function for private writing and ITPR for private reading together on the network overhead on both client and server sides. We compared 2BPS to 3 different BIR-based anonymous group communication protocols, which are Repost, Blinder, Blong. We chose these protocols specifically because they rely on BIR and provide provable cryptographic anonymity guarantees similar to BPS. Here, LS refers to the length of the sent message, and R refers to the length of the retrieved block. We can see here from the overhead in this figure. This figure showed the total communication cost to send one message and retrieve one block by the client. Here we vary the number of the clients and retrieve the size of the retrieved block. From the figure, it's clear that the bank introduces a high communication overhead, and this is because bank relies on computational BIR, which is more expensive than ITBIR that we use in to BPS. Repose and blinder as well require communication cost is much higher than to BPS because they broadcast the messages to all clients, while to BPS supports selective multicast communication. And here also we discuss, or we the figures illustrate the network download of 2 rounds. We can see that the broadcasting is extremely inefficient, and also the tongue in terms of the network download overhead. We evaluated the broadcasting based on our we evaluated 3 different assumptions of the number of the cover traffic. So the first here means that all the sent message are real message. Here 50% of the sent message by the clients to the server are real messages. The server, of course, drop the fake messages and forward to the clients all the real messages. This maybe when we have less amount of real messages, that means less amount of messages that will be forwarded to the users. Anyway, here also we can see that 2PBS is better than broadcasting, even when the number of subscribed topics per client increases. From these figures, we can learn that adopting ITPR in our protocol to retrieve the interesting messages generally allows bandwidth efficient communication between the client and server, which makes the 2PBS suitable for bandwidth restricted users. In this slide, we evaluate the efficiency of our protocol in terms of latency. Here in the first figure, we can see that the retrieval time of one block, how it scales when we vary the block size and the number of the clients. In general, we can see that there is no big difference between the retrieval time of broadcasting and 2PBS, but 2PBS is much faster than PANG in retrieving blocks. Also here we present the retrieval time when we vary the number of subscribed topics per client. You can see still that the difference isn't that big between the 2PBS and broadcasting. And from these 2 figures, we can see that the 2PBS retrieval method can reduce the bandwidths, like what we mentioned in the previous slide, that the 2PBS retrieval method can reduce the bandwidths without leading here and retain to high latency, even if the clients have many subscriptions. The last figure showed the end-to-end latency for posting one message when we vary the number of clients. Again, this figure demonstrates that the retrieval time doesn't affect that much the latency, and so we can find that the 2PBS the latency here of 2PBS is slightly smaller than the system that uses distributed point function in broadcasting. But the 2PBS is extremely better than blinder and repost, and also it with performance bond, especially when we have a modest number of users or clients. To conclude the talk, 2PBS is a new anonymous published subscribe protocol that provides private writing using distributed point functions and private reading using information traffic PIR. It protects against strong adversary to ensure sender and receiver and observability, or publisher and subscriber and observability. The evaluation results demonstrate the efficiency of WPS in terms of latency and bandwidth compared to similar or related systems. For future improvement, we aim to improve the auditing protocol to distribute trust on many servers without introducing a high overhead. And also we are interested in enabling the users to subscribe to multiple topics using one subscription request. Finally, we think it's a good idea to allow the user to anonymously retrieve the messages from previous rounds. Thank you.